Hello everyone. Today I want to show you something that begins with a very simple sequence of numbers but leads us to a very beautiful mathematical constant. Let me start with 0, 1, 1, 2, 3, 5, 8, 13, 21 and so on. This is the Fibonacci sequence. The rule is very simple. Every number is obtained by adding the previous two numbers. See, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21 and so on. Now I want to do something slightly different. Instead of looking at the numbers themselves, let's divide the consecutive numbers. For example, let me divide. For example, 2 divided by 1. So it will be 2. Similarly, 3 divided by 2. It will be 1.5. Then 5 divided by 3. 5 divided by 3. 1.667. 1.667. Now if I divide 8 by 8 divided by 5, what will I get? If I divide 8 divided by 5, I'll get 1.6. Similarly, 13 divided by 8, we get 1.625. Similarly, if we divide 21 by 13, we'll get 1.615. 1.615. Now let's keep doing it. Now after 21, the next Fibonacci number is 34. And after 34, when we'll add 34 with 21, the next Fibonacci number is 55. So now we'll divide 34 by 21. So if we divide 34 by 21, we get 1.619. And if we divide 55 by 34, we get 1.618. Now if you can notice certain things, please notice the numbers are getting closer and closer. See, closer and closer to what? Closer and closer to a number called 1.618. So this number 1.618033988 and so on, this number is called the golden ratio. This is called the golden ratio or the divine ratio. And today I want to understand why. Let's forget Fibonacci for a moment. Imagine I have a line and I am going to divide it into two parts. For example, I have divided it like this. Let the longer part be A and let the shorter part be B. The golden ratio occurs when the relationship is A plus B upon A, the longer part, will be equal to A upon B. The ratio of the whole to the larger part is same as the ratio of the larger part to the smaller part. And this is called, the ratio is equal to phi. This is called phi. So now let's derive it. A by A plus B by A is equal to phi. Now a plus a will get cancelled, so it will be equal to 1 plus b by a, which is equal to 5. Now you can see a upon b is equal to 5. So I can write b upon a will be equal to 1 upon 5, right? So instead of b by a, I am going to write 1 by 5. So 1 plus 1 by 5 is equal to 5. And now I will multiply this whole equation with 5. So what will I get? 5 into 1 will be equal to 5 plus this will get cancelled, so it will be 1, and it will be equal to 5 into 5 will be equal to 5 square. So finally I got a quadratic equation, and the quadratic equation is 5 square minus 5 minus 1 equal to 0. So finally we got this quadratic equation. Now using the quadratic formula, we will solve it. And when we will solve this using the quadratic formula, we will get the value of 5 equal to 1 plus minus under root 5 upon 2. Since we are talking about a positive ratio, we take the positive solution, so we will ignore the negative part. So if we solve it, so we will take the positive value, so 5 will be equal to 1 plus root 5 upon 2, and when we will solve this thing, we will get the value of 5 equal to approximately equal to 1.6180339887. It's an irrational number. So this is what we get the golden ratio, and it is not just a magical number. It comes directly from a very simple geometric relationship. Now let's take the mathematics and turn it into something we can actually draw. For convenience, I am going to use a 10 centimeter square as my starting point. I don't want to try to measure 16.18 centimeter with a ruler. Instead, I am going to construct the golden rectangle geometrically. So let's start. So it is a 10 into 10 centimeter square. Now I will take the midpoint of this side, that is 5 centimeter. So I have marked the 5 centimeter, which is the midpoint of this line, and now I am going to connect it with this. So you can see we got a right angle triangle with base as 5 centimeter and perpendicular as 10 centimeter. So the hypotenuse will be equal to 5 square plus 10 square under root, which will be equal to 5 root 5, and whose value is approximately equal to 16.18 centimeter. So you can see this is my golden rectangle. Its dimensions is 16.18 centimeter and the width is 10 centimeter. Let me highlight it. So now again we can divide this rectangle into a square..
'Let me do it. So now again we can divide this rectangle into a square. Let me do it.
So now again we can divide this rectangle into a square. Let me do it. So now again we can divide this rectangle into a square. Let me do it. So now again we can divide this rectangle into a square. Let me do it. So now again we can divide this rectangle into a square. Let me do it. See, again, we got a square and a rectangle, and this rectangle is also a golden rectangle. Now, if I further divide this rectangle into a square, we'll again get a golden rectangle. Let's see. So can you see? I got another golden rectangle. Now if we further divide this golden rectangle again into a square, we'll again get a golden rectangle. Let's see. Can you see? Again we got a golden rectangle. So actually this whole is a golden rectangle. Now why it's called a golden rectangle? Because if we divide the sides, that is 10 centimeter, to the longer side 16.18 centimeter, we get approximately 1.618, and this 1.618 is the golden ratio. And then again, after removing this square, when we got this rectangle, this is also a golden rectangle, because again the proportion of its sides also has the same ratio, that is 1.618. That is why we again and again get the golden rectangles. So I've already made these squares, and now I'm going to arrange these squares over them, and then we'll see some pattern. So it is like this. Now we'll keep removing the squares one by one. Okay, so let me remove this square first. When I remove this square, we got this, and this is what the golden rectangle. When this was attached, this whole was a golden rectangle. But when from this golden rectangle I removed the first square of 10 into 10 centimeter, we got another golden rectangle. Let's do it again. Let us remove another square. So this is another square, I'm removing it. Now you can see again this structure. This is also a golden rectangle. Now if I remove another square, again this structure is also a golden rectangle. If I remove another square from this, again this is a golden rectangle. See, this is also a golden rectangle. And now again if I remove a square out of it, again I will get this rectangle, and this rectangle is a golden rectangle. I hope it's clear. So golden rectangle, remove squares, smaller golden rectangle, remove squares, smaller golden rectangle. So this property is called self-similarity. And I think this is one of the most beautiful properties of the golden ratio. The shape contains smaller version of itself. You can see. Now let's return to Fibonacci. 0, 1, then 1, then 1 plus 1 2, then 2 plus 1 3, 3 plus 2 5, 5 plus 3 8, 8 plus 5 13, 13 plus 8 21, 21 plus 13 34, 34 plus 21 is 55, and so on. So it's Fibonacci sequence for us. We also discovered that f n plus 1 upon f n is equals to the golden ratio, that is phi. In other words, as the Fibonacci numbers become larger, the ratio of the consecutive number approaches 1.61833, which is the golden ratio. We can also do one thing. What we can do is we can make squares whose side lengths are the Fibonacci numbers, like 1 into 1 squares, then 2 into 2, centimeter squares, then 3 into 3 centimeter square, then 5 into 5 centimeter square, 8 into 8 centimeter square, and 13 into 13 centimeter square, and we try to arrange them. So if we do this, we'll get something like this. See, I arranged 1 into 1. This is 1 into 1 square, 1 into 1, so there are two 1 numbers. Then the another Fibonacci number is 2, so I made a 2 into 2 square and then arranged it here. Then after 2, the next Fibonacci number is 3, so I made a 3 into 3 square and placed it below this. So 2 plus 1, you can see 3. Then the next Fibonacci number is 5, so 3, so I made a 5 into 5 square and I placed it here. So you can see 3 plus 2 is also 5. Then another next Fibonacci number is 8. I made a 8 into 8 square, placed it. Then next is 13, so I made a 13 into 13 square and then placed it here. And then I joined the corners of these squares, and you can see we got a beautiful spiral like pattern. And also this is a Fibonacci rectangle, and its dimensions are 13 into 21. So 21 upon 13 is approximately equal to 1.61538, which is not exactly the golden ratio, but it is closer to the golden ratio, that is 1.618, right? As we make more squares, larger dimension squares like 34, 21 and 55, 34, so we approach this number. So from this we can make make a connection that Fibonacci numbers are associated with the golden ratio. We have seen the golden ratio mathematically. We have seen it in the Fibonacci ratios. We have constructed it in a rectangle. But now let's ask a different question. Do we also see this pattern in the world around us? Just look at this. We often see golden ratio spirals or rectangles superimposed on the human faces. Some proportions of the face can be close to golden ratio relationships, but human faces vary enormously. So we should not claim that every face is a golden ratio face, but we can see the same pattern. Sunflowers are another fascinating example. Their seeds form a spiral pattern, and Fibonacci numbers can appear in the number of spirals in the different directions, clockwise and anti-clockwise. Here the connection with Fibonacci mathematics is much more meaningful, but again it is not necessary that every sunflower has exactly the same numbers. Now look at this. Even fingerprints are sometimes shown with a golden spiral overlays. We can see the pattern. Can you see the resemblance with the pattern, with the spiral? And then we also have these enormous structures such as the spiral galaxies. They can look remarkably, you can check, they can look remarkably similar to the mathematical spirals. But a visual resemblance doesn't mean that the galaxy is literally constructed using the golden ratio. Now I want to move from rectangles to another beautiful geometric figure, the 5-pointed star or the pentagram. I am going to construct a regular pentagon first. For my demonstration, I have used 10 centimeter for each side of the regular pentagon. So all these sides are 10 centimeter each, and it's a regular pentagon. Now these are the diagonals. If we'll join all these diagonals, so in total there are 5 diagonals in a regular pentagon, 1, 2, 3, 4 and 5. So there are 5. So I have already drawn the diagonals. You can see if the diagonals are visible. So this I have joined with this diagonal. I have joined this diagonal, diagonal number 1. Then diagonal number 2, you can see. then diagonal number 3, then diagonal number 4, and then diagonal number 5. So there are 5 diagonals in total, and if we join them, if you can see, we get a shape of a 5-pointed star. So I have made it. So if you will cut it, you will get a star like this. I am placing it here so that you can easily recognize it. Now comes the mathematical surprise. In a regular pentagram, this is called a pentagram. So in a regular pentagram, the lengths created by the intersections of the golden ratio relationships. So they are following golden ratio relationships. For example, if I take the longer side and divided it by the smaller side, it will always be equal to 1.618. So once again the number 1.618 appears in geometry. This is important because it shows us that the golden ratio is not only an algebraic formula, it can be seen in the geometric relationships. Now I want to make a connection that I personally find very intriguing, and I want to be careful about how I present it. In descriptions and modern interpretations of the Mahamrityunjaya Yantra, we encounter geometric elements including a 5-pointed star, this is the 5-pointed star, and lotus petal forms. For my demonstration, I am going to construct a simplified geometric representation inspired by those elements. A central 5-pointed star, 8 petals surrounding it, and 3 eyes-like elements associated symbolically with Lord Shiva. And then there is another number I find interesting, that is 13. Now Trayodashi literally refers to the 13th lunar day, and Mahamrityunjay practice is associated with the Trayodashi in some traditions. Now let me show you the yantra, and this is where mathematics meets symbolism. At the center, I have represented 3 eyes associated with Lord Shiva. Then look at this star. At the center, this is the 3 eyes of Shiva. Around them, it is a 5-pointed star constructed from the diagonals of a regular pentagon. You see, this was a pentagon, and I joined the diagonals and made a star out of it. So 5-pointed stars, 1, 2, 3, 4, and 5. And then around the star, there are 8 petals, 8 lotus petals, 1, 2, 3, 4, 5, 6, 7, and 8. Now look at these numbers: 3 eyes, 5-pointed star, 8 lotus petals, and remember Trayodashi. Trayodashi means 13th day of the lunar month, because the ritual of Mahamrityunjaya mantra is mostly associated with Trayodashi. Now look at these numbers: 5, 3, 5, 8, and 13. They're all the Fibonacci numbers, you can see. The symbolism here is an interpretation of the design, not a mathematical proof of a religious tradition. But as mathematical artwork, it gives us a beautiful opportunity to see how numbers, geometry, and symbolism can be brought together. Is it not interesting? Now, there can be many reasons why numbers such as 3, 5, 8, or 13 appear in a tradition. Maybe mathematical, symbolic, astronomical, ritual, or simply coincidental. So we should not confuse an interesting pattern with a proof of historical intention, but I think the pattern is still worth showing. So let's look at the journey we have taken. We started with 1, 2, 3, 5, 8, 13, and 21, a very simple sequence. Then we looked at the ratio and discovered that they approach 1.618033. We also derived the number mathematically. Then we constructed the golden rectangle, if you remember. We constructed this golden rectangle. This is the golden rectangle. Then we also removed all these squares and discovered self-similarity. Then we looked at the Fibonacci square. We looked at this Fibonacci square and saw why Fibonacci rectangles approach the golden rectangle. Then we constructed a pentagram. We constructed a pentagram. This is a pentagram. We constructed this and found golden ratio relationships within its geometry. And we finally looked at an intriguing numerical correspondence 3, 5, 8 and 13 of the Mahamrityunjaya Yantra in the context of an Indian geometric symbolic tradition. And perhaps the most important message I want to leave you with is this: the golden ratio is not magic. It is not a secret code that automatically explains everything in nature, art, architecture, or even spirituality. It is a precise mathematical relationship. If you remember, it is phi equal to 1 plus root 5 upon 2. We also derived it. What makes it fascinating is that this simple relationship connects algebra, geometry, and the Fibonacci sequence. And when we encounter similar patterns in art, architecture, or cultural traditions, we can appreciate them. But we should also ask, is this mathematically demonstrated? Is there historical evidence, or are we simply noticing a pattern? Because mathematics is not only about finding patterns, it is also about asking whether those patterns are actually meaningful. So we begin with something as simple as 1 plus 1 equals to 2. You remember Fibonacci sequence? 2 plus 1 equal to 3. So we begin with this. And all this led us to phi equal to 1 plus root 5 over 2, and to one of the most beautiful ideas in the elementary mathematics, and this is the golden ratio. Thank you so much. If you enjoyed discovering the hidden history of mathematics, don't forget to like the video, subscribe to Happy to Help Tutoring, and tell me in the comments which hidden mathematical story would you like to explore next. Until then, keep learning and stay curious. Goodbye.